In this video, we're solving an optimization problem where we're trying to minimize the travel time between 2 points. Now, ordinarily, the path that minimizes the travel time between 2 points is just a straight line. But in this problem, we have two different velocities. So the setup for the problem is that we're on an island 1 mile offshore, and we're trying to get to a shop that's 3 miles down the beach. And I've labeled in the diagram a horizontal distance from our initial position that I called x, and that's how we're going to locate our landing spot on the shore. So in the problem, we're told that we can swim at 2 miles per hour, and we're told we can walk at 3 miles per hour. And again, we're trying to find the minimum travel time to get between these 2 points. Now we can consider a couple limiting cases here. One of those is that I could swim straight to the shore to minimize my swimming time since my swimming speed is slower. And the problem with that path is that I end up covering more total distance than I have to. Another limiting case is that we could consider just swimming straight to the store. And that minimizes my total travel distance, but then I'm spending all my time in the slower medium where I can only swim 2 miles per hour. So somewhere in between at this spot X, I'm going to find the path that minimizes my travel time. And what we want to do is try to express the travel time as a function of X, and then we'll take the derivative and set equal to 0 to find that special landing spot. Before we get started, I want a quick reminder of the relationship between distance, speed, and time. So I'm going to write that as d equals vt, where that's v for velocity. And this means provided the velocity is constant, that a travel time will be d over v. So on each leg of this journey, we're going to have a different travel distance, a different travel speed, and then we can express the travel time. So we'll go ahead and start by writing down the travel distance for the swimming part of the journey, and that's just the hypotenuse of a right triangle. So I end up with the square root of x squared plus 1 for that. And then we need to write down the distance that I walk in terms of x. So if my total horizontal distance is 3 miles, and I've already covered x miles of the horizontal distance while I was swimming, that leaves 3 minus x additional miles to walk down the beach. So now I can write down the travel time for each leg of the journey. So I'll just use a t1 for my swimming time. And that's going to be the distance I spent swimming, which is the square root of x squared plus 1, divided by my speed when I was swimming, which is 2. So I'm just going to write this as a 1/2 out in front. So there's my swim time. And then I write down my walking time, which again is just distance divided by speed. So this time it's 3 minus x divided by 3 miles per hour. And I'll write that as a 1/3 out in front. So now my total travel time, I'm going to call that t of x because it's a function of x. It depends on where I land on the beach. This is just going to be t1 plus t2, which is 1/2 square root x squared plus 1 plus a 1/3 times 3 minus x. And using a computer to plot that function, we can see that we're actually looking at a minimum value somewhere around here. So our travel time is going to be minimized when x is just a little bit less than 1 mile. So it's worth mentioning the two limiting cases that we talked about earlier. When x is 0, that's where I swim straight to the shore and then walk 3 miles down the beach. I can see that that takes longer. And the other one is when x is equal to 3. In other words, we swim straight to the store, and I can see that takes even longer. So to get to this minimum value, that's a local minimum of the function. So we just take the derivative and set equal to 0 and solve for x. So taking the derivative of this thing, I have t prime of x. And x squared plus 1 square rooted is the same as x squared plus 1 to the 1/2 power. So then I follow the power rule and I say that's 1/2 times x squared plus 1 to the negative 1/2. But don't forget the chain rule. I have to differentiate the interior function here, and that gives me an extra 2x. Then in my second piece, if I just imagine distributing the 1/3 before I differentiate, the first term is going to be a constant, so that's gone. The second term is a negative 1/3 x, which differentiates to just negative 1/3. All right, so these 2's are going to cancel in my first term. And I'll go ahead and write my first term as just a single fraction. So I'm going to get rid of the negative exponents. And I have an x in the numerator, and then a 2 times x squared plus 1 to the 1/2. In other words, square root of x squared plus 1. And then I have this leftover term minus 1/3. And what we're doing here is setting this all equal to 0 in the search for that local minimum value. So I can move that 1/3 over to the other side, and I get x over 2 square root x squared plus 1 is equal to 1/3. Then I can multiply both sides by the least common denominator here. So in other words, I'm going to multiply both sides by 3, and then I'm going to multiply both sides by 2 square root x squared plus 1. So on the left, I'll have a 3x, and on the right, I'll have a 2 square root x squared plus 1. Now I can square both sides to get rid of that square root, and this gives me a 9x squared is equal to 4 times the quantity x squared plus 1. So I can distribute that 4 and then combine the like terms. So I have a 4x squared on the right-hand side. I'm going to subtract that from both sides, giving me a 5x squared on the left. And then I have a leftover 4 on the right. Finally, I divide by 5 and then square root the result. So I end up with x equals 2 divided by root 5. Or if you want to rationalize that, it's going to be 2 root 5 over 5. So it's useful to get a decimal approximation on this number just to make sure our answer is reasonable here. And this x value turns out to be about 0.894. So a little less than a mile right of where we started. So that was the only question that we were asked in the problem, like where do you land to minimize your travel time? But we might as well continue and figure out what that minimum travel time actually is. And then we'll go back and compare to the graph of t and see if we agree with it. So I'm going to evaluate t of 2 root 5 over 5. And when I sub that in to the square root part of t, I have to square x. And this is where I kind of regret rationalizing this thing. Remember, it was written as 2 divided by root 5, and when I square that, I get 4/5. Or we can square the rationalized version, and we get 4 times 5 over 25, which reduces to the same 4/5. Then in my second term, I have a 1/3 times 3 minus 2 root 5 over 5. All right, 1 is 5/5. So in this radical expression, I have a square root of 9/5. And then distributing my 1/3, I have a 1 minus 2 root 5 over 15. And we continue to simplify here. When I take the square root of this numerator, I get a 3. I have 1/2 times 3 over root 5 plus 1 minus 2 root 5 over 15. And rationalizing that first piece, I get 3 root 5 over 2 times 5, which is 10. And then we have a plus 1 and a minus 2 root 5 over 15. So it looks like our common denominator is going to be 30 here. So I end up with a 9 root 5 multiplying by 3 over 3 in this first fraction. So 9 root 5 over 30 plus a 30 over 30 minus 4 root 5 over 30. So combining the two radical terms there, I get a 5 root 5. And I have 5 root 5 plus 30, all divided by 30. Now that certainly doesn't mean as much as a decimal approximation in terms of interpreting our answer here. So getting a decimal approximation on this, we find that our total travel time is going to be about 1.37 hours. So taking one last look at our total travel time function here, we found that our minimum travel time is achieved when x is 0.894 miles, in other words, about 0.9 miles. So we're talking about something like this for our x value. So that's 0.894 miles. And I can see a local minimum in the travel time function at that point. And then our y value corresponding to that, in other words, the total travel time, we found that that was about 1.37 hours. In other words, slightly less than 1.5 hours. And given the grid units here, where this is 1 hour, that looks like a pretty reasonable approximation. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.